video in my new house. So let's see how it goes. If you like these videos, please take a moment to subscribe, like, and share. It just takes a moment, and it's the only way to let YouTube know that you like them so more people can see them. The more people watching and commenting, the more we will all learn, so please participate. Okay, so there's one more important concept that we have to explore before we learn the definition of a topology, and that is finite and infinite sets and countable and uncountable sets. So you would imagine at first blush that finite sets are the easiest thing in the world. We have a set with 3 objects. What's hard about that? But actually, there's a lot of interesting logical issues involved even with finite sets. And actually proving even the most basic facts about finite sets is quite involved, and it requires real manipulation of the concepts of functions, like surjective, injective, and bijective, and the inverses of functions, and so on. So this is a really interesting topic that will give us some more exposure to and practice with the methods of proving a theorem involving a function's bijectivity. So we're going to do that now, and then next time we'll look at infinite sets, and then we'll be ready to define a topology. So in this video, we will prove one lemma and one theorem. The result we're working toward, that the cardinality of a finite set is uniquely determined by that set, will follow in the next video as a corollary to this theorem. This video is split up into 4 sections. First is a discussion of why finite sets are so logically subtle and not as obvious as they seem instinctively. Then we prove the lemma. Then, before the proof of the theorem, we'll have some more discussion. The proof of the theorem involves some very subtle and roundabout logical argument. Once we understand the logic behind the proof itself is pretty simple, but understanding why we proceed the way we do requires a lot of thought. So after the lemma, the middle part of this video is a lengthy discussion of the reasons for the steps of the proof. Then the end of the video is the actual proof. So there's one definition at the root of the concept of finite sets. For any positive integer n, the set of positive integers less than n is called a section of the positive integers. So there's nothing controversial about that. All that is giving a name to sets of integers from 1 to n. Okay, so this is called a section, and it would be denoted by Sn. If you know any abstract algebra, you'll recognize that this symbol has another meaning relating to groups and symmetrical groups, but forget about that for now. That doesn't have anything to do with this. It's just another meaning for this for now. I'm going to try not to use this because we can just use this, but anyway, the set of positive integers from 1 to n is called the section. It's called a section of positive integers. Now, so these sets from 1 to n are the prototypes for what we call finite sets. The study of finite sets is basically devoted to proving that every finite set is a bijection with a unique section of positive integers. Okay, so definition. A set A is said to be finite if there is a bijection between A and some section of the positive integers. That is, A is finite if it is empty, or if there is a bijection f from A to the set from 1 to n, for some positive integer n. If A is empty, we say that A has cardinality 0, and if there's a bijection with a section n, then we say that A has cardinality n. So, for example, the set from 1 to n itself has cardinality n because there is a bijective correspondence with itself under the identity. Okay? Okay. Sound good? No. We've already run into a logical problem that shows just how crazily subtle math can be. And this is why I'm enjoying these proofs, and I think that they're really important for us to do, because getting into these subtleties now will help us prepare for when the math gets more difficult. So the problem here is that we have not shown that the cardinality of a finite set is uniquely determined by the set. For all we know, so far, there might be two different sections from 1 to n and 1 to m that have bijective correspondences with our set A. So there could be two bijections, one with 1 to n and another with 1 to m. So that's a really subtle and difficult thing to wrap your head around. We're suggesting that if we have a bag of marbles and two people count the number of marbles in the bag, that it's possible that they'll come out with different answers and both be correct. That's ridiculous, right? But it's our everyday intuition that tells us that it's ridiculous. It would be easy to prove if the bag had 1 or 2 or 3 marbles. We could even physically watch each person count the marbles and verify that they are the same. But what if we had a box with 5 million marbles? So how would we prove directly how many marbles exactly are in that box? If you counted 1 marble per second, it would take 60 days to count 5 million marbles. So let's say we had a boxcar full of marbles. Let's say we asked 10 people to count the marbles in this boxcar. So a boxcar can hold around 70 million marbles, approximately. It would take each one of them over 2 years, counting nonstop, to count the marbles in one boxcar. So they'll almost surely come up with different answers, right? But how is it possible that they come up with different answers? There's two possibilities. So one, obviously, is one of them made a mistake. But here's the problem with that. That assumes that we know the actual number of marbles in the boxcar. And we're comparing the different results to the real answer. But there's another possibility. It may be that there actually do exist bijective correspondences between the marbles in the set and two different sections of positive integers. Maybe it's possible to map two different sets of natural numbers, 1 to 1 and onto the set of millions of marbles. Maybe. It's something we have to prove. Or we have to prove that that isn't the case. Because all we have so far are 10 people counted them and they came up with different answers. We don't know why. It might be that one of them made a mistake. We can't know that because we don't know how many marbles are in there. Or it could be that it's possible that all of them are correct. We have to prove that the latter is not true. So when we say that obviously one of the counters is wrong, we're making an assumption. It's an extremely strong assumption, backed by years and years of experience here on Earth, right? Because every time we've tried to count a collection of objects, it always comes out to the same number, no matter how many times we do it. But that isn't a proof. So in real life, we would just accept the first explanation, someone miscounted. We have an intuitive belief that we can count small sets accurately, so it must be true for big sets as well. But in mathematics, we can't take intuition like that on faith. If we formulate the question in terms of the existence of a bijective correspondence, rather than the physical act of counting, then it will be capable of mathematical proof. We will prove in a moment that if m does not equal n, then there cannot be two bijective functions, one mapping a to n and another mapping a to m. So to me, the important thing about this exercise is, moving forward, is to contemplate how do we go about recognizing when we're making an assumption such as this. Failing to recognize leaps in logic is what leads to failures in proofs. Andrew Wiles made a mistake in his proof, and as a result, he had to share credit with Richard Taylor. He could have been the one guy that proved for Matt's last theorem, but he screwed up, and so he had to share credit with someone else. He was right at the end, and he had to share credit. In this case, I think you might be able to see pretty quickly what's missing from this definition. We didn't say that there's one and only one bijection. If we had, it might have pricked up our ears a little more quickly, and we would have said, now wait a minute, how do you know that, right? The definition is simply that if there is any section in bijective correspondence with the set, then it is defined to be finite. Okay, so the goal of this video is to prove that indeed the cardinality of a finite set is uniquely determined by the set. It's actually going to take us quite a lot of effort to prove this intuitively obvious thing. But as I said, it gives us a good opportunity to get some practice manipulating sets and using sets and functions in proofs. Okay, so first, a lemma. So this lemma is the foundation of our proof that the cardinality of a finite set is uniquely determined by the set. Let n be a positive integer, let A be a set, and let A sub 0 be an element of A. Then there exists a bijective correspondence F of the set A with the set of integers from 1 to n plus 1 if and only if there exists a bijective correspondence G of a set A minus A0 with the set 1 to n. All this lemma is really saying is that if there's a bijection between A and a subset of integers, and you add one element to A, then you'll have a bijection with 1 to n plus 1. And if you have a set A with a bijection from 1 to n plus 1, and you subtract an element, you'll have a bijection with 1 to n. So all it's saying is that for every finite set, if you add 1, then the cardinality is going to go up 1, and if you decrease 1, the cardinality is going to go down 1. Okay, so it's if and only if. So we need to prove it in both directions. So let's do the second part first, and then we'll do the first part. So first we'll assume the second one and prove the first one. So we assume that there exists a bijection from A minus A0 to the integers from 1 to n. We need to prove that that implies that there is a bijection from A to the set 1 to n plus 1. So let's define a function f from A to the set of integers from 1 to n plus 1, where fx equals gx for all x that are in the smaller set, and then if x equals a0, we assign that to n plus 1. Okay, so this is obviously bijective because we started by assuming that G is bijective for the set A minus A0. So we just set f equals G for all the x up here. And then we only have one more element to deal with, which is A0. We set that to n plus 1, and that's all there is to it, okay? So that part was easy. Okay, so to prove the converse, assume there exists a bijection f from A to 1 to n plus 1, and we have to prove that there exists a bijection from A minus A0 to 1 to n. So we have an A0. Either f maps A0 to n plus 1, or f maps A0 to some other number. If f of A0 equals n plus 1, then it's easy, because if we just take f restricted to the set A minus A0, f restricted to some subset is written this way. So this means we're looking at f over this domain rather than the full domain of A, okay? So if we just restrict f to A minus A0, then that is a bijection from A minus A0 to 1 to n, right? Because the only element left is A0, which is going to n1, n plus 1, so we just remove that one. Okay, but if f of A0 maps to anything else, then let's just let f of A0 equal m. Now, in that case, because this is a bijection from A to 1 to n plus 1, if A0 doesn't map to n plus 1, then there has to be some other element that maps to n plus 1. So let's let A1 be the point such that f of a1 equals n plus 1. Okay? So now we know that a0 does not equal a1. So now we can define a new function. Okay, let's forget about this. I'm going to do this on the next page, so I need to have more room. Okay, forget about this. So we're just going to define a function, h, from a to 1 to n plus 1. So we're going to set h of a0 to n plus 1, which equals f of a1. And then we're going to set h of a1 to m, which equals f of a0. And then for everything else, we're just going to let h of x equal f of x for all the other elements in the set except for a0 and a1. So basically what we have here, so f maps a0 to m and a1 to n plus 1. And h maps a0 to n plus 1 and a1 to m. Okay, so all we're doing is switching the 0 and the 1. And now we started by assuming that f is a bijective correspondence. So we can see that h is also a bijective correspondence, right? Because it's the same as x, except two additional elements, which are the only two left. So h is also bijective. And now with h, we're back to the easy case, because now we have a function, it's a bijective function with n plus 1 that maps a0 to n plus 1. So if we just let g equal h restricted to a minus a0, then this is the same as we did before. Then this is the desired bijection between a minus a0 and 1 to n. So that's it. So this next theorem is the main result for finite sets. It doesn't quite prove that the cardinality of a set is uniquely determined, but after this theorem, that result follows closely behind. Let A be a set and B be a proper subset of A. Suppose there exists a bijection f from A to 1 to n for some n in the positive integers. Then 1, there exists no bijection g from B to 1 to n. And 2, provided that B is not the empty set, there does exist a bijection from B to 1 to m with m less than n. Okay, so this theorem tells us two things. If B is a proper subset of A, then there cannot be a bijection with B and the same section of integers as A. But there will be a bijection with a smaller section of integers than A's. So this theorem is basically saying that if the set is smaller, then the bijection must be smaller too. Okay, so proof. Okay, so first, if B is the empty set, then there's nothing really to prove, because if B is empty, then there cannot be a bijection between an empty set and a non-empty set. One's empty, the other's not. There can't be a bijection between them. And then the second half doesn't apply when B is empty. So that's it for the empty set. Now, so to prove the theorem when B is not empty, we're going to use induction. So the initial step is to prove that the theorem is true when A has cardinality of 1. That is, n equals 1. So in this case, A consists of a single element, A. So its proper subset can only be the empty set, right? And we've already shown the proof when B is the empty set. So basically, there's nothing to do if A only has one element, because the only possible proper subset is the empty set. So for the induction step, let's go to the next page. So assume the theorem is true when A has cardinality n. We need to prove that it's true for n plus 1, right? Okay, so Suppose that f from a to 1 to n plus 1 is a bijection. Okay, so wait, what? What are we doing here? This proof starts in a very confusing way. At first glance, it looks like I just told us to assume the thing that we're trying to prove. Right? We're supposed to assume n and prove n plus 1. Then the first thing I do is say, okay, let's assume n plus 1, right? What's going on? It took me a long time to get my head around what we're doing here. Because the thing to remember is we're not making any claims about A and its bijection with n plus 1. The claims of this theorem are about subsets of these sets. So we're given the bijection between A and n plus 1. The question is, assuming the theorem is true with a set with a bijection with n, then what can we demonstrate about a bijection with n plus 1? So this is why the lemma is so important. The lemma shows us another fact about finite sets, a different one from what we're doing here. And that is that if you have a finite set of cardinality n, then there is another set of cardinality n plus 1, and another set with cardinality n minus 1. So basically, because of this lemma, we already know that there's like a cloud of finite sets. There's one that has cardinality n, n plus 1, n plus 2, n minus 1, n minus 2, and so on. So all the lemma establishes is that if there's one finite set, then there's another one bigger and another one smaller, and so on down to the empty set. That's what the lemma showed us. So when we start by assuming that there's a bijection between A and n plus 1, we're not making a statement related to the theorem at all. All we're doing is saying, okay, so there is some set with a bijection with n plus 1, and hence there's another one with n, another one with n minus 1, and so on. What we're assuming for the induction step is that if there is a set with cardinality n, then that set does not have a proper subset that also has cardinality n. Okay, that's the assumption that we're making. That's the induction step. So we know that by assumption. And we know furthermore from the lemma that if there's a set with cardinality n, there also has to be a set with cardinality n plus 1, n plus 2, n minus 1, and so on. So using the assumption about subsets of a set of cardinality n, we'll be able to use that assumption to prove that the theorem must also be true of a set with cardinality n plus 1. Okay? So basically, it might be possible that there are no finite sets with cardinality n at all. But if that's true, then there are basically no finite sets. But if one of them exists, then an n plus 1, n plus 2, etc. exist as well. So all we're saying here is, yes, assume that finite sets exist. Then the lemma means that there's bigger ones and smaller ones and so on, okay? Because otherwise there's nothing to talk about. We've talked now about why proceeding this way is sound, but we haven't talked yet about why we need to proceed in this way. Remember that the point of the theorem is about proper subsets B of A. So we have to suppose a proper subset of A without putting any restrictions on it. If we started with a set with cardinality n, and then we added an element x to it in some way to make a set with cardinality n plus 1, we can't move forward from there. Like, we can't do anything with this. Because if we choose a subset of this larger set, a plus x, and so just for the moment, just pretend that this makes sense, okay? Because it doesn't actually make sense. There's no such operation, but you understand what I mean. It's like it's a set one bigger than A. If we create the bigger set in this way, we have to make statements about any proper subset of this set. But if we try to take an arbitrary subset of this, the subset may contain X or it may not contain X, and we haven't established anything about B here. Because there's nothing we can work with. We don't know anything about B. It's just some subset of this, but is X in there, is X not in there? And we haven't gained anything here, okay? So for that reason, it won't work to start with a subset of cardinality n and add one element to it. And then there's an additional problem, which is that this operation a plus x has not been defined at all. And there's a lot of other problems with it because we know a, but what is x coming from? Is x an old car? Is it pi? Is it the set of all sets that do not contain itself as a subset? We don't know anything about x. So that's just another logical sort of stumbling block here. And further, x might already be an A. Because what we really need to say is that A union x, where x is not an element of A. That's what we really want to say. But this is just all very messy, and it doesn't help us anyway. And this is, I think, the reason that set theory has a minus operation, but not a plus operation, because it leads instantly to exactly the kind of logical conundrums that we're trying so hard to avoid here. So minus avoids all of this because we're starting with the universe of elements in A, and then if we take one away, that's all perfectly sound. Okay? Okay. So anyway, this is why we're starting with a set that has cardinality n plus 1. All we're really saying with using the lemma is that finite sets exist. And then the lemma tells us that one of cardinality of every size exists, so certainly that includes n plus 1. Then we take an arbitrary, non-empty proper subset of A and choose an element A0 from this subset. From there, because now if we choose an element from this one, then we know that it's also an A, and everything makes sense. From here, we'll be able to quickly use the lemma and the induction assumption to prove that if a set of cardinality n does not have a proper subset of cardinality n, which is the induction assumption, then the set of cardinality n plus 1 cannot have a proper subset of cardinality n plus 1 either. Okay, so you can see now why I wanted to take the time to prove these statements about finite sets. They require extreme logical care to avoid falling into a morass of logical dilemmas. And this set theory is the foundation of topology. And topology is the foundation of all calculus, and real analysis, and vector analysis, and hence complex analysis. And hence Weierstrass equations and elliptic curves, which are at the root of Weyl's proof of Fermat's last theorem. Okay. So starting again with the induction step. We're assuming that the theorem is true for sets with cardinality n. We need to show that it follows that the theorem is true for sets of cardinality n plus 1. So again, suppose that f from A to n plus 1 is a bijection and that B is a non-empty proper subset of A. Okay, so now choose an element A0 that is in B and an element A1 that is in A minus B. So A minus B means everything that's in A that's not in B, right? So A1 is out here and A0 is in here. And we know that A1 exists. We know that A minus B is not empty because B is a proper subset, which means that there has to be something in A that's not in B. That's the definition of a proper subset. So A1 exists. Now, note also that B minus A0 is a proper subset of A minus A0 because A1 is not in B, so it's not in B minus A0, but A1 is in A minus A0. And since B is in A, then B minus A0 is a proper subset of A minus A0. Okay, so now the lemma tells us that if this is a bijection, then there also exists a bijection G from A minus A0 to 1 to n. So now this is a bijection from 1 to n. So that means by our induction assumption that the following two statements are true. 1, there does not exist a bijection h from b minus a0 to 1 to n. And 2, either b minus a0 is empty, or there does exist a bijection k from b minus a0 to 1 to p with p less than n. This is all from the induction assumption step. Because we have a bijection from 1 to n, then we know that these two things are true, right? B minus a0 is a proper subset, so it cannot have a bijection with 1 to n, but it does have a bijection with 1 to some number p with p less than n. Okay, so now we can apply the lemma to these two pieces of information. So the lemma tells us that if there is a bijection from b to n plus 1, then there must be a bijection from b minus a0 to 1 to n. Now the contrapositive of that is that if this is not true, then this cannot be true. Okay? And 1 tells us that indeed there is not a bijection from b minus a0 to 1 to n. That means from the contrapositive of the lemma, this cannot be true. So the lemma tells us that there cannot be a bijection from b to n plus 1. And that was the first half of what we wanted to prove. We wanted to prove that if A has a bijection with n plus 1, then there cannot be a bijection with a proper subset of A and the set 1 to n plus 1. Okay? That was the first half of what we wanted to prove. The second half of what we want to prove is that there will be a bijection between B and some number smaller than n plus 1. So first note that if B minus A is the empty set, then there is a bijection from B to the set 1, right? Because if B minus A0 is empty, then B only has A0 in it. So there's a bijection between A0 and 1, okay? So if it's empty, we're done. Now, if B minus A0 does not equal the empty set, then we can take part 2 of the induction assumption, which says that there exists a bijection from B minus A0 to some other number P with P less than n. And now we can apply the lemma again. If there's a bijection from B minus A0 to P, the lemma tells us that if there's a bijection between B minus A0 and P, then there has to also be a bijection between B and P plus 1. And then since P is less than n, then P plus 1 is less than n plus 1. I messed this up. Let me do this again. So we've shown that in either case there exists a bijection from 1 to m with m less than n plus 1. Because m either equals 1 or m equals p plus 1, which is less than n plus 1. And that was what we needed to show. For any set A with a bijection to 1 to n plus 1 and a non-empty proper subset B, there exists a bijection of B with 1 to m for some m less than n plus 1. Okay, and we're done. We've shown that the theorem is true when n equals 1, and we've shown that if we assume the theorem is true for n, then it's also true for n plus 1. That means by induction, it is therefore true for all n in the positive integers. Okay, and that's what we wanted to do for today. Next week, we will complete the proof that the cardinality of a finite set A is uniquely determined by the set A. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.